Hello students, this is the third part of the diffraction phenomenon, and in this lecture I have included the circular aperture and double slit. In the last lecture I have discussed about the plane wave incident on a long narrow slit of width d, and due to the diffraction of light wave the emergent wave spreads out along the width of the slit, that is in the direction of the lesser width in comparison to the other dimensions which are greater in comparison to that width, and the angular distance is lambda by d, and the spread is 2 lambda by d, where d is the width of the slit. But if I would suggest you to watch the last video on the single slit Fraunhofer diffraction that I have said for better understanding of this part, especially the second part of this lecture, which include double slit interference diffraction phenomenon, Fraunhofer diffraction phenomenon due to double slit. Okay, you can check that one and then join with this video. So first part is the circular aperture. The arrangement for observing the diffraction pattern through a circular aperture is this one. Here we have a lens. This is the aperture, circular aperture. Plane waves are incident normally on the aperture, and a lens is placed near the aperture, but the diameter of the lens is much greater than in comparison to the circular aperture, and we due to the rotational symmetry of the system, we will get concentric bright and dark rings on the screen, which is placed at the focal plane of this lens, and this pattern is known as airy pattern. The plane wave is incident on the circular aperture. Fraunhofer diffraction pattern is observed on the focal plane of the lens, and due to rotational symmetry of the system, the diffraction pattern will consist of concentric bright and dark rings, which I have shown in the figure, and these rings are this pattern is known as airy pattern. And the angular spread, actually the derivation of the diffraction pattern for circular aperture is quite somewhat complicated. So the final result for the angular spread of the beam is approximately delta theta is equal to 1.22 into lambda by d, where d is the aperture diameter of the aperture. Now the simple example is two stars that has equal irradiance in coherent in distant point objects seen through the objective of a telescope, and our intention is to know what would be the diameter of the aperture, so that we could see the two stars separately through the telescope. So what should be the diameter of the aperture of the telescope? If two stars has angular separation delta phi, and if delta phi is much more greater than delta theta, the images of the two stars will be easily resolved. That is, we can see the two stars distinct, and separate images of the stars will be found on the focal plane of the telescope. Let us into the this is the angular separation between two stars is delta phi, the light coming from the two stars going through the aperture of the telescope, and this is the angular separation of the one star delta theta, and this is the other star delta theta. So if delta phi is much more greater than delta theta, the image of the two stars will be found on the focal plane of the telescope. According to Rayleigh criteria, the stars are said to be just resolved when the center of the airy disk falls on the first minima of the airy pattern of the other star. What does it mean? If the two stars approach, I will explain it after this slide. If the two stars approach to each other, their respective images come together, overlap with each other, and we will get a single blend of image, single blend of fringe pattern, and thus we will not be able to see the two stars separately so far. And according to Rayleigh criteria, they will be just resolved if the center of one airy disk falls on the first minimum of the airy pattern of the other. Here is the image. This is the image of clearly resolved diffraction phenomenon, and this is Rayleigh pattern. The center of the one is fall on the minimum of the other, first minimum of the other, then it will be said that it is just resolved. That is what said in the Rayleigh criteria. Okay. The minimum resolvable angular separation or angular limit of resolution is delta phi is equal to delta theta is equal to 1.22 lambda by d. And if this distance is delta L, if delta L is the delta L minimum has the value 1.22 f lambda by d, and delta L is the center to center separation of the images, that is this distance is delta L. And the resolving power of any image forming system is generally defined as 1 by delta phi minimum or 1 by the reciprocal of delta L minimum. So resolving power of a telescope can be increased by increasing the diameter of the objective lens. That is, if we increase the diameter of the objective lens, that is by increasing f. Here lambda is taken as constant, but we can not also by decreasing the value of d. If we decrease the value of d, then the resolving power will increase. Also by increasing the value of f, we can increase the resolving power. And by increasing the focal length of the diameter of the lens helps to collect more of the incident radiation. So by increasing the diameter of the lens, we will be able to get sharper and brighter image, but of smaller in radius of the image. Thus we will get airy disk of smaller radius but of higher intensity. Let us consider the case of human eyes, and let us take the aperture of the human eye as 2 millimeter, and for bright condition, under bright condition, lambda is taken as 550 nanometer. So if we calculate the value of delta theta by putting in this expression delta theta or delta phi, 1.22 for lambda, 550 nanometer, and for the 2 millimeter, we will get it, the value of this as 1 arc minute. Let us take another example. So delta theta is 1 arc minute, and let us take another example. Okay, and if f is the focal length of the human eye is taken is about 20 millimeter, then the delta L minimum, it comes around 6700 nanometer. Let us take another example. Consider Hubble Space Telescope. For that, the aperture diameter is around 2.4 meter and the focal length is 57.6 meter. So if we calculate the delta phi, by putting these values in this expression for delta phi, we will get that it is nearly equal to 0.5 arc second. That is half of an arc second. Also, by decreasing the wavelength, we can decrease delta phi and correspondingly increase the resolving power, because the expression that we get is delta L equal to 1.22 f lambda by d. So lambda has a function which will increase or decrease the resolving power of the instrument. So, using ultraviolet rather than visible light in microscopy allows for perception of finer details. The electron microscope utilizes equivalent wavelengths of about 10 to the minus 4 to 10 to the minus 5 that of light. This makes it possible to examine objects that would otherwise be completely obstructed by diffraction pattern in the visible spectrum. Now, the question comes, if the telescope it has high resolving power of the order of half of the arc second, angular separation can be identified, then what is the necessity of sending satellite to the space? We know that the atmosphere has different layers, and different layers at different concentration, different refractive indices. So the light that receives the telescope from the source, it comes from different positions for different time and makes the image of the star bigger than the original one. So it's better to send satellite rather than observing through the telescope. Now the second part, double slit. Suppose that we have two slits of width b, width, that means the width along this direction, this is z direction, along this direction these two slits have the same width b, and the center to center separation between the two slits is taken as a. The two slits are so the separation between two consecutive points can be taken as a plus b, and the ray diagram of these is shown in this diagram. The plane waves are incident on the two slits, and the slit widths are b, and they are separated by distance a, and the each aperture would generate the same single slit diffraction pattern on the screen. Here, same primary wave exerts the secondary source at each slit, so the resulting wavelets will be coherent, and thus interference must occur. If the primary wave is incident on the aperture at an angle theta, that means the angle with the normal is theta, the angle is theta, then there will be a constant relative phase difference between the secondary sources. But at normal incidence, the wavelets are all emitted in phase, and we know that the interference fringe at a particular point of observation is determined by the differences in the optical path lengths traversed by the overlapping wavelets from the two slits. Here we would find that the resultant intensity distribution is a product of the single slit diffraction pattern and the interference pattern produced by two point sources separated by a distance a. So if the diffracted rays make an angle theta with the normal to the plane of the slits, then the path difference between the two disturbances at a point P will be delta sine theta, and the corresponding phase difference is phi equal to 2 pi by lambda delta sine theta. I have discussed all these about these things in the last lecture, so you must go through the last lecture. Let the two aperture or the slit is divided into differential strips dz along z axis, as we have considered this axis along the z axis. So the total contribution of the electric field in the Fraunhofer approximation can be written as E tilde is equal to E naught tilde. This is a constant part, and integration from minus b by 2 to plus b by 2 e to the power ikz dz plus E naught tilde integration a minus b by 2 into a plus b by 2 e to the power ikz dz. You can understand this expression if you go through the last lecture. And for the expression for E, that comes A is equal to sine beta by beta cos alpha and cos omega t minus beta by 2 minus phi by 2, where alpha, we get two terms alpha and beta. So alpha is equal to pi by lambda A sine theta and beta is equal to pi by lambda B sine theta. So if we multiply both sides 2, so 2 alpha, that gives 2 pi by lambda A sine theta. We know that 2 pi by lambda sine theta is the 2 pi by lambda sine delta sine theta or A sine theta or B sine theta, whatever may be, that gives the phase difference term. So this must be a phase difference, as it includes A, and A is the separation between the two slits and the distance between the two slits. So this is the phase difference between two waves arriving at P, one having originated at any point in the first slit and the other coming from the corresponding point in the second slit. So this term alpha comes from the two slits, and 2 beta is similarly 2 pi by lambda B sine theta, as it includes B, and B is the width of the one slit. So phase difference between two nearly parallel rays arriving at a point on the screen from edges of one slit. And when averaged over a relatively long interval in time, the intensity term takes the form I function of theta is equal to I 4 I naught sine square beta by beta square cos square beta, and we can write this as 4 I function of 0 sin square beta cos square alpha. If theta equal to 0, that is for normal incidence, we can write alpha is equal to 0, also beta is equal to 0. So I theta, sorry, okay, I naught, actually I function of 0, it gives the value 4 I naught, and I naught is the intensity distribution from either slit. And the intensity distribution pattern looks like this. Why it looks like this, I will explain it. If KB is very much less than 1, what is K? You have to understand from the last lecture. The link is given in the description box. Please go and check that lecture, then you will be better, will get the better understanding. Okay, if KB is very much less than 1, that is beta is very small, and we assume sine beta by beta is nearly equal to 1, then I theta, it comes 4 I function of 0 cos square alpha, because sine beta by beta is taken as 1, since beta is very small for this condition. And this gives the expression for intensity distribution of Young's experiment. Okay, if you remember, this cos square alpha terms gives the Young's experiment expression, intensity distribution for Young's experiment. So this term is corresponds to the interference pattern. And if A is equal to 1, that is the two slits coalesce into one, and alpha is equal to 0, then I function of 0 is equal to 4 I naught, and in that case cos alpha becomes 1. So it is equal to 4 I naught sine square beta by beta square. And from the last lecture we have seen that these terms corresponds to the single slit diffraction phenomenon, Fraunhofer diffraction phenomenon, with double the source length. So this gives the expression for single slit diffraction phenomenon with double the source length. Then we must envision the total expression as being generated by a cos square alpha term, that is interference term, modulated by a sine square beta by beta square, that is sin square beta term, which is the diffraction term. So this is the interference term, and this is the diffraction term, and that's why we have got this type of fringe pattern. This part corresponds to the central maxima. This gives the diffraction phenomenon, and these are the minimas and the first maxima, second maxima, and in between the inside the central maxima, these fringe, these are the interference pattern. We have beta is equal to pi by lambda b sin theta and alpha is equal to pi by lambda a sin theta. If we put beta is equal to m pi, then the condition for diffraction minima will be achieved. So b sin theta comes from this expression. If we put beta equal to m pi, we get b sin theta equal to m lambda, and also the condition for minima can be achieved if interference minima can be achieved by putting a sin theta equal to n plus half lambda. The interference maxima occur when alpha is equal to 0, pi, 2 pi, etc., or when a sin theta equal to 0, lambda, 2 lambda, etc. The actual position of the maxima will approximately occur at the above angles, provided the variation of the diffraction term is not too rapid. Also, a maximum may not occur at all if theta corresponds to a diffraction minima. Okay, let's move to the last image. Okay, you can see that this is the central maxima and these are the interference pattern. So at this point, when the first minima of the diffraction pattern occurs, we cannot observe the interference pattern at this position. So at this position, the interference maxima is absent. So it is called the missing order. Let for a slit, B is equal to 0.0088 centimeter and lambda equal to 600 Armstrong. The first diffraction minimum will occur at theta is equal to lambda by B. This is for the single slit. For single slit, we have seen that the expression for theta will be lambda by B for the first minima. So putting that, we get it is 0.389. So this is the first minimum of the diffraction pattern. So interference maxima are extremely weak, around 0.4. I have written 0.4, that is around 0.389 degree. So you can see that if the for that example that I have taken as B as 0.0088 centimeter, for that the position of the first minima of the diffraction pattern is around 0.4 degree. So at around 0.4 degree, the interference pattern will be not prominent, and that can be said as the missing order. Okay. Let us take B is equal to 8.8. This is a homework for you. Let us take B equal to 8.8 into 10 to the power minus 3 centimeter. A is equal to 7 into 10 to the power minus 2 centimeter, and lambda is equal to 6000 Armstrong. How many interference minima will occur between two diffraction minima on either side of the central maximum? This is your homework. Do it, and my students, you can interact with me through the WhatsApp group, and for others, you can write your answer on the comment section. Okay, thank you for watching.